Now, though the integral test is kind of difficult to apply most of the time, it has a bunch of conditions, you gotta do an integral. There are some of the results that come from the integral test that you can sort of put it in its own box and use it without having to integrate over and over again. And this is one of them. So this is the p-series test. So this type of series that you see right here when you have 1 over n to the power p, p being a constant, this is called a p-series. So p-series. So a p-series is a series that has this exact format, 1 over 3 n to the power p, and it will converge if p is big enough, and it will diverge if p is not big enough. So all values of p, including p equal to 1, p less than or equal to 1, will make this series diverge, and p greater than 1 will make this series converge. And the reason for that is very simple. Like I said, it's the integral test. So if you go ahead and integrate the function 1 over x to the power p dx from 1 to infinity, that will be, so as long as p is not 1, so let's say this is in tube hearts, if p is not 1, then this is the integral x to the power negative p, 1 to infinity dx. So you add 1 to the power. So that's minus p plus 1 is the same as 1 minus p, and divide by 1 minus p from 1 to infinity. This is the reason why I needed p to not be 1, because I want to divide by the new power. And you can see that p, if p is bigger than 1, right? P is bigger than 1. P bigger than 1. This number becomes 1 over 1 minus p times x to the power p minus 1. So whenever you have a number on the numerator, or a power of x on the numerator of a fraction, you can bring it down by changing its sign. So this is what you have. You evaluate it from infinity to 1. So if p is bigger than 1, then this is a positive exponent. And so when I plug in infinity, basically I take a limit of this. This will be 0 minus plugging in 1 is 1 minus p. So I just get this. So I just get 1 over p minus 1, which is finite. And so the series converges by the integral test. Okay, if p is less than 1. Now, if p is more than 1, if p is less than 1, it converges if p is more than 1. Now, if p is less than 1, right? If p is less than 1, then this right here from this step, if I pull this from here, p less than 1, x 1 minus p over 1 minus p infinity to 1. This is already positive because p is less than 1. 1 minus p is positive. So when I plug in infinity, x to a positive power, it's going to be like an x squared or an x cubed. So this is going to be infinity. So the series will diverge, again, by the integral test. And finally, the only third possibility, which is when p equals 1. This is the integral 1 to infinity 1 over x dx. That is the natural logarithm of x from 1 to infinity. And just taking the limit, this is already infinity. So this diverges. This is also the harmonic series. So whenever you see the harmonic series, you can say that it diverges by the p-series test, of course. But the harmonic series on its own is more important than p-series in general, so we don't usually say that. We say that it is the harmonic series and that it diverges. It's more important. Being a harmonic series is more important than being a p-series, if that makes any sense. Okay, so I hope this shows what I'm trying to say. Whenever n to the power p is dividing, if p is big enough, so you're dividing 1 by n to a big power. So you're getting small things. And so P big means the series converges. P small less than or equal to 1, the series diverges. And now I don't have to do all of this green math calculation here that you see. I just use this theorem number 5. Just say by the P series test, it diverges or it converges. So let's do an example. It's going to be pretty short, pretty quick. Here, this is a P series. P equal to 5, which is more than 1, so it converges. This is a P series. P equal to the square root of 2, which is about 1.4, which is definitely more than 1. So this converges. So pretty quick, pretty simple. Now this one is not as simple, but one step further is not hard to see. See, this is that. So this is a P series. P equals 0.999, which is less than 1 this time, so the series diverges. And this one, same thing. You can bring it up or bring it down, n to the power 1.1. Again, it's a P series, so P is 1.1, which is more than 1, so the series does converge. So I think this is pretty interesting, and you can solve these examples pretty quickly. This is one of my favorite tests to use because it's so immediate, so clear. I can immediately tell that a series converges if I see that it is a P series or if it diverges, right? Because I can tell by the P value. Now, I told you just now that 1 over n is a P series, the harmonic series is a P series, and that it diverges. Another important characteristic of the harmonic series is that among all P series, it is the first one that diverges. So as long as you keep the powers here big enough, if you have 1 over n squared, 1 over n cubed, 1 over n 1.1, 1 over n 1.00001, all of those here converge because P is just bigger than 1. It's just enough for it to converge. Repeat the integral we did at the beginning if you don't believe me, right? But starting from this one, everything here on that side will also diverge. So it doesn't matter how many 9s you put here. This diverges. And then, of course, if you try n to the power negative some power, of course, this is the same as just n cubed. So it does diverge. So everything here diverges for smaller n. So the harmonic series is also this important sort of comparison standard that you can set other series comparable to, so make them comparable to the harmonic series. We're going to talk about the comparison test in a little bit, and so this is a good idea to have, but for this video, mostly just think about the P series, identifying, recognizing, and finding the value of P.